In the previous module, we have looked at the representation of periodic signals using complex exponentials. To be very specific, we have looked at the representation of periodic signals using a set of harmonically related complex exponentials. So what we have obtained was the expression x p of t, that is a periodic signal. Any periodic signal can be represented with the help of linear combination of harmonically related complex exponentials. So we have e to the power j, integer multiple of some frequency. That frequency is called as a fundamental frequency, and let me make a small change in the notation. Instead of omega, I will write that as omega naught, indicating that this omega naught here is what is called as a fundamental frequency. Now, to understand this representation, let's take an example. Let's take a periodic signal, very simple as say x of t equals to say cos two pi t. Very simple signal. Now we know what is omega here. This omega here is 2 pi. Now we'll realize that after representing this complex, the periodic signal in terms of complex exponential. So let's try to represent this periodic signal with the help of complex exponential. Now from basic math, we know that this periodic signal cos of theta can be represented with the help of Euler equation. That means x of t, we can represent that as using Euler equation as half e to the power j 2 pi t plus half e to the power minus j 2 pi t. Now if we relate this expression with the original one, we can see that this is also a linear combination of complex exponentials, where this k times omega here is 2 pi, and the coefficient here ak's are half. If we compare this with this, you can see that the coefficients here, this 2 pi is nothing but the omega, so omega naught here is 2 pi, whereas the k here, just because there's nothing here, so the k remains 1, and here the k will be minus 1, so the k here is going to be 1 and minus 1, so ak here, that is the coefficient for k equals to 1, is half, and the coefficient for k equals to minus 1 is again half. So that is going to be ak equals to a of minus k. So a k here is 1. So we have a1 equals to a of minus 1 equals to half. So we can see that the periodic signal, that is cos 2 pi t, is represented as a linear combination of this complex exponential, and we can see that the coefficients, the Fourier series coefficients, can be obtained as the coefficients of this complex exponentials. So here in this case, if x of t is cos 2 pi t, the coefficients are half and half here. So there is only one k that is present, and rest of the k's, as k is running from minus infinite to infinite, there are no other k's that are present in this signal. So here there is only one k that is present, where what is the k? K is 1 and the minus 1, both are the same as half. So we have the k value as 1 and -1 there, and rest of the keys are 0 in this case. Now let's try to understand what this representation says. This representation simply splits the periodic signal into complex exponentials. Now this is very simple case of a periodic signal. Let's suppose if we have some different periodic signal, say for example if we have cos x of t equals to cos 2 pi t plus cos 4 pi t. So let's have this signal. Now again with the similar approach, what we can see that x of t can be represented as half e to the power j 2 pi t plus half e to the power minus j 2 pi t. So these two terms refer to the first component, that is cos 2 pi t, and plus the rest of the components, say e to the power 4 pi t plus half e to the power minus j 4 pi t. So here also we have the linear combination of complex exponentials, and the same is represented here. We have a periodic signal being represented as a linear combination of complex exponentials, and we can see that here the fundamental frequency is 2 pi, and the coefficients here, this is the coefficient for k equals to 1, that is a1. This is the coefficient for k equals to -1, just because here k is -1, so this is a -1. What about this? This is the coefficient for a2, just because this is 2 times 2 pi, so that is k times the fundamental frequency, that is omega naught, and this is a of -2. So we have the complex exponentials and their coefficients. So the Fourier series says the same thing. We can represent a periodic signal using the linear combination of these harmonically related complex exponentials. Now let us try to visualize what we have seen here. For that purpose, I am having this animation that is available at fallstat.com. You can see this animation that is available at this link. Now what I have done here is to visualize a typical sine wave. Now the sine wave is appearing something like this, you can see that. Now this sine wave is having, or often for that matter we can take cosine wave also, because we have seen the example of cos wave and we have seen that. So let me make this some changes here in the visualization, some settings here. Alright, so let's take this example, what we have seen here. The first example that we have seen, the first example was cos 2 pi t. So if we have a cosine signal with the frequency of 1 Hertz, that is omega as 2 pi, that is going to be something like this. So we have this signal as cos signal, and that is having the magnitude as 1. You can see that. So this axis here, you can visualize those as the k axis, the small k axis. So this component indicates k equals to 1. The first component indicates k equals to 0, the second indicates k equals to 1, the third component indicates k equals to 2, and so on. So this axis here, it is k. Now let's take the second example. The second example here, we have seen that the second example we have two such cost signals. One, it is present at frequency 1 Hz, and another signal is present at 2 Hz, just because it is 2 times 2 pi. So let's try to visualize that here. So we have this component in red. In addition to that, we have one more component. So let's make that component. So we have the component of 2 Hz there. So like this. Now I'm having two components. You can see in visualization that the signal in yellow is the signal that is available of 1 Hz, and the second signal that is again in yellow is the signal with frequency of 2 Hz. So we have first signal with 1 Hz, we have the second signal with 2 Hz, and we have the addition of them. The resultant signal is going to be there in this red. So we have this resultant signal. You can see that this resultant signal is also going to be periodic. The original signal, that is this red signal, the red signal is now being decomposed into two signals. You can see that the signal with 1 Hz and signal with 2 Hz. When both of them are added, we get the resultant signal as this red one. So I can represent that again. So if I'm having a signal of say 1 Hz, I'm having another signal of 2 Hz. When both of them gets added, you can see the change in the waveform that is happening. If I add the second signal, you can see that the change that is happening here is in the shape of this signal. So the resultant signal is going to be periodic, and it will have those two components, the signal with 1 Hz and the signal with 2 Hz. And what is this? This is the K, and the height of this K indicates the amplitude. So if we reduce the amplitude, you can see the change in the waveform, the resultant waveform. Let's try to add one more component here. So if we add a frequency component with 3 Hz, you can see the change in the waveform. So the resultant signal is again periodic, and it is having now 3 components. So the axis here is K, and I am simply changing the coefficient or the magnitude of K. So if we go back to this expression, you can see that this magnitude here, this coefficients I am changing, and the frequency components I am adding them. So like such, if I go on adding various components, I'll get different signals, and that too, those signals are periodic in nature. Those signals are going to repeat after a duration that is the t. Now let's have some random signal. Let's say if I'm having a triangular signal, you can see that if you have a triangular signal, you may see that there are all such components here. You can see these components here. If it is triangular signal, you can have these many components. So we have a signal with 1 Hz, we have a signal with 3 Hz, we have a signal with 5 Hz, and so on. Let's take a random signal that is periodic. Let's say a signal that is periodic with random shape. So let's say I'm having a signal something like this. Now you can see that so many components are present here. Now again, let me change the shape. Let's say I'm having the shape of the signal as something like this. You can see that these components are present in the signal. So if you want to see these components, you can simply hover over this. So you can see that this is the original signal with 2 Hz. This is getting added with another signal that is of 4 Hz, 6 Hz, 8 Hz, and so on. All these components, when added together, you'll get the resultant waveform that is there in the red. So what this Fourier series says is, you give me any periodic signal. So here I have taken this triangular shape periodic signal. So if there is any periodic signal, that periodic signal can be decomposed or can be represented with the help of sinusoids. A complex, or we can say that can be expressed as a linear combination of complex exponentials. So this is the complex exponential magnitude that I'm changing, and you can see that corresponding waveforms are getting added to get this resultant triangular waveform. So like such, we may go for different signals and see how the representation looks like. Let's suppose if I'm having a square wave, something like this, you can see that these many components that are present in this square wave. So we have the frequency of 1 Hertz that is getting approximated, and we have another frequency, we have the third frequency, and so on. If you observe this graph very closely, you can see that the first component with respect to which the signal is decomposed, it is actually the close resemblance with the original signal. So if you have only one component there, it is the closest approximation to the signal that we are trying to decompose. The other components, if added together, will get the signal under consideration, that is the signal in the red. So that is the significance of Fourier series. The Fourier series says you give me any periodic signal. So let's suppose this is a triangular signal that we are having. Any signal can be decomposed into a set of linear combination of harmonically related complex exponentials. So this is a complex exponential with frequency say 1 Hertz. This another complex exponential with frequency say 3 Hertz, and so on. So if you add them together, you will get this triangular signal. So that's a visualization of Fourier series. We shall see more into this in the next module. See you then.